Okay, so we were looking at the out-of-class exercises dealing with logarithms and solving these exponential models for specific values. So I'm going to look at these out-of-class exercises for M6. And I'm going to look at number 1 here. Number 1 says, Jose deposited $2,500 in a CD. Annual percentage rate, APR, of 3%, compounded annually. So you must leave it in the account for at least 5 years. Now that part, the at least 5 years, doesn't mean so much to us when we're making the model. Now we've worked at making these generic models. Remember, this is what we called an exponential model. Can anybody tell me why it's called an exponential model? Well, remember, our other type of model we had was a linear model. Yep. And why was that called a linear model? Yep. And when we graph it, what shape does it make? Yeah, either a sloping up or sloping down line. So it makes a line on the graph. So it's called a linear model because on the graph it forms a line. Now the exponential model wasn't named after the shape on the graph. It was named after the form of the equation. The equation for an exponential model has an exponent in it. And the key with an exponential model is, remember, an exponent has 2 parts. It has a base and a power. In an exponential model, the variable is in the power. We haven't really discussed it yet in this class, but if the variable is in the base, that's a polynomial model. That was one, if it was in the base, we could solve it using roots. When it's the variables in the power, we have to solve it using the logarithms. Okay, so we could make this model, actually this one, since it's compounded annually, we could probably write the model without the equation, but we kind of got cut off last time, so I wanted to take a little bit of time to review the model for compound interest. I'm going to flip back just to make sure I use the same variables that the book does. Okay, so your amount that's in the account is equal to the principal times 1 plus your interest rate divided by n to the power of n times t. Now, most of this formula is pretty self-explanatory. The principal, what does the principal stand for? In this problem, it would be 2,500, yes. And that is always the starting amount. And yes, definitely the 2,500 in this problem. What does the R stand for? Either in this problem or in general. The rate. And for this problem, that would be, careful. Rate is always going to be the 3%. Very good. Hi, Sarah. No problem. And then, of course, I'm going to jump to T. T stands for, the time in years. And the 5 years can come into play in this problem in certain circumstances. If we're looking for we can look for other time periods in this problem. The trickiest one is N. N stands for The number of what? You've got the right idea. It's the number of periods in a single year. Well, in this case, this is compounded annually. So how many times does it compound in a year? 1. So in this problem, it would be 1. So that depends on the compounding. If it was compounded monthly, it would be 12. If it was compounded quarterly, it would be 4. So now for this problem, we're looking for the amount. We said that the principal was the 2,500. What's going to go in for R here? .03, yep. Yep. And then divided by, I'm going to write it like this instead of over the top because this is how it looked when we enter it in our calculator. Divided by 1, then to the power of, well, 1 times t. We don't necessarily know 5 years is the minimum it has to be in there, but we don't necessarily know what year we're looking for. Now, in the first part of this question, part A, it does ask how much would they have at the end of 5 years. So t would be 5 for part A. And what did you come up with for part A? Now, for me, a lot of times it's easier if I just multiply this out so I can enter it in my power as just 5 when I type it in the calculator. What'd you guys end up getting? Anybody want to be brave? Yep, should be the 5th power. Yeah, 28, 98, 19. Okay, 2,898.19. Now what you come up with, okay. Well, let's go through punching it in here. You'll have to punch in. There, now I can see it. So you got a really weird number? Okay, well, let's do this one together. So you do 2,500 times, make sure you hit your open parentheses, 1 plus 0.03 divided by 1, close the parentheses, then to the power of, like I said, I just do the 1 times 5 and I enter 5 so that I don't have any issues in that power. Did it come out better that time? Okay, perfect. This is something I want to come back to, these examples of investment at the end of the class if we have free time. These are a couple of pretty important things that I'd like to show you. For now, let's take a look at the next part, part B. How long would it take for the account to surpass $4,000? So how long does it take for A to be $4,000? So this means that we're going to put 4,000 in for A. And we're solving for, no problem, we're solving for T. Now again, since this is 1 times T here, I'm just going to write it as T. So to solve this for T, what's my first step? we're going to solve this formula right here for t. So we need to get t by itself. Now, to get t by itself, the first thing we have to do is isolate the exponential. Remember, the exponential is the base and the power. So t here is the power. The base is this. This is the base of that exponent. So the first thing we have to do is get rid of what? Well, we have to get rid of the 2,500. Very good. So we divide there. This ends up being 1.6 equals 1 plus 0.03 divided by 1 to the power of t. Once we have isolated the exponential, our second step is to do a logarithm. Now remember, the log that we're going to have to do is going to be base whatever the base of the exponent is. So remember, the exponent has those two parts. It has the power, this is the power, and it has the base. This part is the base. So I'm going to combine those numbers in there for right now. 1 plus 0.03 divided by 1 is just 1.03. So the base of this exponent is what? 1.03. So to solve this, we have to do a log base 1.03. Now remember, our calculator only does log base 10. So if we have a base here, if this is different than 10, does anybody remember the formula we used for adjusting the base? No? Okay. So it's the log base a of b is log of b divided by log of a. So it's log of this number here divided by log of the base of our logarithm, 1.03. Over here, the log and the 1.03 cancel out. That's just going to give us t. So you have log of 1.6. Make sure you close your parentheses. Divided by log of 1.03 gives us 15.9 years. No, we're just learning this. In another week, we should know this. In another week, you should, but right now, we're still in the process of learning it. Yeah. Well, well, it is a different way of thinking. You know, the roots and stuff like that are things you've all seen before. For many students at this point, this is the first time they've seen the logarithm. So it is a new concept. So it'll take you a while to get used to it. Now, just a reminder, by the way, that we do have coming up, is it next week, Thursday, something like that, that we're going to do? Yeah, next week, Thursday, we're looking at doing our Unit M test assessment in class. What'll happen is we're going to do M7 today, M8 on Wednesday. Next week on Monday, I want to take some time. I want to go back and make sure that we've reviewed M1 and 2 because those were done before I started here. So I want to make sure you guys have those. Then we'll take the rest of that class to review whatever we need to. And then, yep. Yep, that is fine. Yep, that is fine. And usually what I do is I give you, so that you don't have to rush to make corrections on stuff like that. Usually what I do is I give you till like the class after our test. because there won't be any homework after the test. That way, instead of homework, you can work on those corrections if you need to. So like 2 weeks from today would probably be my deadline on those corrections. Okay, so number 2 I wanted to take a peek at. The reason I want to take a peek at number 2 is number 1 was exponential growth with the compound interest. Number 2 is decay, depreciation. So at number 2, we have a car that depreciates at 10% per year. And that goes for 5 years. The starting value of the car was $22,234. So let's create this model. Now, this isn't compound interest, so we don't have a standard template, but we still have our standard form of an exponential where we have the amount is equal to some beginning amount times 1. Now, is it going to be, it's either going to be plus or minus here. Which one is it going to be in this case? Minus. Why is it minus? It's depreciating. The value is decreasing. Very good. So then what's the rate? It's depreciating at 10%, so it's going to be minus 0.1 or 0.10, and then to the power of t again, since this is time. So the model for this one, what's the beginning amount? Sure, go ahead. Well, this is not compounded interest. So this is just annual. Yep. The n only comes in there if we're breaking down the period, that compound interest. So what's our beginning amount here? Perfect, 22,234. Kind of a strange starting amount, huh? And what I'm going to do is I'm going to go ahead and combine this here. The 1 minus 0.10 is just 0.9, the power of t. Yeah, pretty much. So then what is the balance at the end of 3 years? How would we find that? Well, where does the 3 go? The balance at the end of 3 years, where does the 3 go in our formula? Well, no, the balance at the end of 3 years is just going to be 3 years. T here is just time in years. The fact that this goes for 5 years, all that is telling us is that it goes 10% per year for 5 years. All that's telling us is at the end of 5 years, this model doesn't work anymore. After 5 years, generally with depreciation, after 5 years, it turns into more of a linear depreciation than it does an exponential. So all that is saying is that that's the time in years up to 5. If the time is bigger than 5, we can't use this model anymore. Since this was just 3 years, we can still use the model. So go ahead and try to calculate that balance at the end of 3 years, or if you already calculated it, what'd you come up with? Go for it. 208? Yep, that is exactly what I got. Good job. Anybody have any questions on how we got that? Okay, so that's part A. Part B, how long will it take to depreciate to $10,000? Exactly. Where's the 10,000 going to go into our formula? Okay. I'll give you a chance to beat me to it here. Okay, I'll stop for a second. Yep, the 10,000 goes in for A. Yep. Yes, you're going to get a decimal. That sounds right. Yep. It's going to be log base 0.9. Yep. Yep. Yes. Okay. Okay, so yep, that's the perfect question. Now, yeah. Well, remember when it's log, if this log is not a base 10, we have to do that at base adjustment where it's the two logs divided. So it's going to be a log divided by another log. The top number comes from inside the parentheses. And before you punch that in, I'm going to show you a trick as to how to do that. The bottom number comes from the base of the log. So now, since I have this in my calculator, what I'm going to do is this. I'm going to do log, and then I'm going to do second answer, telling my calculator to take that previous answer, because anything I write down and try to punch back in is going to be rounded off. And then divided by log of 0.9. And I'll see what you guys, what'd you end up with? That's really close. I got 7.58. And it's saying round to the 10th of a year, so 7.6. So you absolutely are perfect. So that process right there of being able to undo an exponential by doing a log is the big concept from last Wednesday. And it's the big concept going forward here with these problems. All right, we will review that a little bit more as time goes on in the next couple of classes. The new concept for today is just applying some of this stuff. We're looking at M7 here, and they're talking about Social Security. And we're going to be looking at it strictly from the mathematical side of it, of course. We're not going to get into any of the politics of Social Security. But as you saw in the preparing for the next lesson, there are some articles on Social Security, how it's been structured and stuff like that. And what we're looking at starting out here with this situation is we're looking at the Social Security system and the funds in what they call the Social Security Trust Fund. This is the money that has been invested. The money that's been collected in Social Security taxes that the government has invested with hopes of keeping the Social Security system operating. That grows at a rate. Currently in 2013, that balance was growing at a rate of 3.8% per year. Now, if you look at problem number 1 in M7, there's a table there that shows in 2013, the growth rate was 3.8%. In 2014, however, that growth rate was 3.6, and in 2015, it was 3.4. What is the rate of change in the growth rate? It's negative, yes. Is it constant? Does it appear to be constant? And how much is it each year? 0.2%. Yep, okay. 0.2% per year. And that is constant. If it truly continues that way, if it is a constant rate of change, what type of model is implied by the growth rate then? What type of model is represented by a constant rate of change? Linear, there we are. That's one of the characteristics of a linear model is a constant rate of change. Remember, it has a constant rate of change and it makes a line on the graph. So the growth rate has a constant rate of change. Now remember, there's a difference. There's two things in this problem that are being discussed. One is the balance in the fund, and the other is the growth rate in the fund, the growth rate of the fund. The growth rate is what's being modeled here. That has a linear model. The balance of the fund has a very complex model at this point that we're not going to try to model. Now, the belief is if this continues, where that growth rate keeps decreasing at that constant rate of 0.2% a year, at some point, it's going to stop growing. How would we figure out at what point it would stop growing? There you go. The percentage is 0%. In other words, 0% growth. So here's what I want you guys to try to do in the next few minutes. I want, based off of these numbers, create a model starting at the year 2013. Create a model for the growth rates. See if you remember the linear equations. I'll give you a couple minutes and then we'll remind you of some things if we need. So, reminder of a linear model. Remember, a linear model has two pieces to it. So the amount in a linear model is equal to, just like in our exponential model, there's a starting point, a starting value, starting amount. But unlike an exponential model, in the exponential model, it's multiplied by a growth factor. In a linear model, it's added or subtracted to a slope times our other variable. In this case, it's going to be time, times t. So what is the starting amount in this model? Well, what was in 2013, what was the value of the growth rate? 3.8, there we go. And now, is it increasing or decreasing? There we go, yes, it's minus 0.2 times t. So, pardon me? That would give you this percent right here. 3.6 minus 3.8 divided by 3.8. That would actually end up giving you a percent. Yeah, that would give you a percent change, which would be, if this were an exponential model, that would be the way we need to find it. But since this is linear, all we really need is the top of this. So now that we have that model, in what year does it stop growing? So I'm going to give you guys a minute or so to figure that out. 19 years, well, let's take a look. So if we solve this, what are we going to put in here to solve this? Perfect. A is 0. And yes, we would solve it then by subtracting 3.8. So negative 3.8 does equal the negative 0.2. And you're absolutely correct. You divide by the negative 0.2 gives us 19 equals t. So that's most of the answer right there, 19 years. But remember, the question was, what year? So one big thing is to always remember to go back and make sure you've answered the question exactly. 19 years from, remember the starting year was 2013. Perfect, 2032. So that was just 2013 plus the 19 years. So 2032 is the year at which this stops growing. Now in the next piece here, they are saying that they believe that when it levels off, it's going to be at $3 trillion. Yeah, that's more money than any of us will see ever. Put it this way, a trillion would be a million times a million. I'm not holding my breath on that one. If any of you guys ever reach $1 trillion in your bank account, I will come and I will manage your money for you at just a 1% per year fee. Okay, sounds good. In fact, I would do it for 0.1% a year. So anyway, what they're saying now is after it levels off, they're predicting it to begin to fall. Now remember, the key term here is decay. It's going to fall, decrease at 8.7% per year. So what I want you guys to do, and we're just going to use 3 for 3 trillion. So I want you to create a model to represent the balance T years after that 2032. So I'll give you guys a minute to see if you can create that model. So what type of model is this going to be? Okay, so the two questions are, okay, we got linear and we got exponential. This one would be exponential, yes. And remember the questions to ask, linear, is it a constant rate of change? Now remember, a constant rate of change that goes down by the same amount, not the same percent every year, or same amount each period. The last one was linear. The growth rate was linear because it was 0.2% every year, no matter what. Exponential is a constant percent change. So it goes by the same percent each period rather than the same amount. So yeah, since this is a percent each period, it is that exponential. So the form of our exponential model, the amount is equal to that beginning value, that beginning amount, times 1 plus or minus that rate to the power of time. Remember that n stuff is only a special formula for compound interest. So for this example, the beginning amount was, we're just going to put in 3 for 3 trillion, times 1 minus, what's the rate that they give us here in number 2? Oh, careful, 8.7. So it's 0.087 to the power of t. So we can simplify this a little bit. I'm going to combine the 1 minus 0.087 to give me 0.913 to get our model. Any questions on where that model came from here? Now, any questions on where that model comes from? Okay. Well, let's see what the first question is here. I guess the first question, part B there, after we found the model, is what is the balance after 1 year? So that means t is going to equal what? 1. Okay. So let's ask. I'm gonna have you guys work on both B and C here. C is the balance in the year 2042. So I'm going to have you guys try both of those, and we'll talk about them in about a minute. So for the balance after 1 year, what's our formula look like? Perfect. And what does that give us? 2.739, and that is in trillion. You got it. I'm sensing a lot of love flowing from Superior today. Whatever works for you. Now for part C, the balance at 2042, what do we put into our formula? Perfect. Now, before we figure this out, where did the 10 come from? Perfect. 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 Yeah, T is starting from 2032. So to get the balance at year 2042, we had to subtract. 2042 minus 2032 is 10 years. So 3 times, actually, I'm trying to think if there's anybody in the world that actually is a trillionaire. And I don't think there is a, yeah, well, I don't think there is a, as I know, in the United States, Bill Gates and Warren Buffett are the 2 richest people in the United States, and neither one of them has reached a trillion. So it would have to be some sort of oil prince. That'd be the only person that I know that would reach that amount. So, what did you get for a balance here today on this one? 1.2? Yep, I actually get 1.207, but probably just a round off. Okay, so 3 times 0.913 to the 10. You'll give up that extra $3 billion? Okay. That's my 1% fee. There you go. Okay, so actually that would be 0.1%, but that's okay. I'm okay with that. Now here's the big one here, part D. How long will it take to reach half of the value? So just remember our model is that. So this is where we've got to bring in what we learned last class with the logs. So I'm going to give you guys a minute or two to figure this one out. So what goes into the formula to figure this one out? We're going to reach half of the value. I guess the question is half of what value? Yes. So half of 3 trillion would be 1.5 trillion. And what's that going to go into the formula for? Well, your beginning value's got to stay 3. That's part of the model. We want the amount to get down to 1.5. Yep. Yep, if you're looking at decaying, radioactive decay and stuff like that, this does apply to that as well. Yep. And what we're actually finding here, I'm glad you brought that up. When we solve this, the T that we're going to get is the half-life of this particular fund. Because most radioactive decay does decay by a certain percent per year. And at the end of that time, if it decays to half of the value, the time it takes is the half-life. Okay, so let's go ahead and solve this. What do we do to solve this? Divide by 3, so it's 0.5. And then we're going to log, exactly. Perfect, log base 0.913. Perfect. Yep. I want to pretend I didn't hear that. So did you come up with 7.6? I'm sorry. So 7.6 years? No problem. Okay. So our next topic now, they are saying that once the balance falls below 500 billion, once it falls below 500 billion, it won't be able to make payments. We hear this all the time. They talk about Social Security becoming insolvent. That term insolvent means there's not enough money to pay out the payments that need to be made. So they figure the balance has to stay at 500 billion just to be able to make out the annual payments that need to be made out of it. So we're looking at, when is this going to fall below 500 billion at the current rate? So when will it happen that we fall below? First of all, 500 billion in our model that we're looking at here, the 3 represents what again? 3 trillion. Yep. Yes, exactly. And that's where I'm going with it. Since the 3 trillion, the 3 is in trillion, any other dollar amount must be represented in trillions, exactly. So, perfect. You could go ahead, ask your question. Yep. Like this? Yep. Yep, that works too. Like the 500 billion. Did I put too many zeros on that? No, I didn't. That's 500 billion right there. So you could look at it like that. Yep. Well, where's the 0.5 going to go in this formula? That's going to be our amount. Remember, once we've created our model, the model isn't going to change. The only thing we can really do within that model is put a number in for t and solve for a like we did up above. We put in t as the number of years we put in to see the balance at whatever year up here. Or we can put in a number for a and solve to see what t has to be. So those are our only two options when we have numbers. So when we have the 0.5 trillion or the 500 billion, that has to go in for a, the amount, the balance. So then how would we solve this? We'll go ahead and do this as a group. Just talk me through it. Divide by the 3. That's 1/6 is actually what that ends up being. 0.5 divided by 3. You did 5 divided by 3. I actually wrote down the wrong number anyway. It should be 1.1. Yeah. Yeah, it should be 0.1666 or 1667. Yep. Yep. Log base. Perfect. I don't know why I put 916 in there. That should be 917, shouldn't it? Or 913. Okay, so you had the log of 0.166 repeating over log 0.913. Now I'm going to pause here. Does anybody have any questions as to where this comes from? Okay, that's the biggie. So we're trying to solve this for t. Because we're solving that for t, we have to do a log that's base this, base 0.913. Do you understand why we have to do a log base 913? Yeah, because our variable is the power in an exponent with the base 0.913. So now, since our calculator only does a log base 10, the log button on a calculator is log base 10, we can't just punch this in our calculator, we have to adjust it. So to adjust it, we take the log of the number that we're solving for, that we're trying to log, divided by the log of that base. So if we have log base a of b, that's log of b divided by log of a. So here, this is a is the 0.913. It's the base of the log. So that's why that goes on bottom. And b is the number that we're taking the log of. That goes on top. That's an important one. I would suggest maybe the front cover of your notebook or something like that, writing that one down, because that's going to be a big one as we go through these exponentials. There's no stupid questions. Go ahead. $1.448 trillion. That would be 1,448 billion. Yep. So what did you get for years here when you did this? Okay, well, let's see what I come up with. I'll do the same thing. I'll do log. What I'm going to do is I'm just going to put in 1 divided by 6 here, divided by the log of, oops, 0.913. I come up with 19.69, so that's close enough. Years. Any questions? Okay. Now the next part is where it gets a little bit trickier. Just what you wanted to hear, huh? So let's go through first of all and say, by the way, actually something I want to point out here. You mentioned half-life. Up in this problem up here, we had found that it takes 7.6 years, right? For it to come in half. So we had the amount equals 3 times 0.913 to the power of t. And we found that half-life, I'm going to put it out 7.615 years. We can actually do a half-life model. Now, you don't have to write this down because this isn't necessarily part of the problem here, but there's an equation for half-life where the amount of a substance is equal to that beginning amount times 1/2 to the power of the time divided by the half-life. So I'm going to take this formula here. A equals 3 times 0.917 or 913. And then I'm going to compare it to this model here, where A equals that beginning amount still going to be 3 times 1/2 to the power of t divided by that half-life we found of 7.615 years. And let's find the balance after 10 years. Now we've already done this with this formula over here. Oops. We already did this. This was A equals 3 times 0.913 to the power of 10. Which is $1.207 trillion. Or trills, as Sarah puts it. The other side, sorry, I couldn't resist. Using the half-life model, it's 3 times 1/2 to the power of 10 divided by 7.615. So the way we would enter this would be 3 times, I'm just going to use 0.5 for 1/2, to the power of, and in my power I'm going to do parentheses, 10 divided by 7.615. And we get the exact same number. We'd solved that up above. We had, if we put in 1.5 for A, which is half of the 3, and we solved this for T. Remember, we divided by 3. Yeah, 0.5. Then we did the log, and it was a log base 0.913. Just a quick review, how do we punch this in our calculator? So we've got the log of 0.913, base 0.913 of 0.5. Remember, there's going to be two logs in this. Sam, do you remember which log goes on top? Which number goes on top? We've got these two numbers. Which one goes on top? Remember the base? Think base and bottom. 0.913. So what goes on top is going to be the 0.5. And if we did that, log 0.5 divided by log 0.913, we got that 7.615. That was our half-life. So I just wanted to point that out. Once we have the half-life, there is another formula involved. That would be this here. I'm going to show you how to go the other way in a little bit if we have some time. So our next question is, assume that it peaks at $4 trillion instead of 3 trillion. Now, how long before it reaches that magical $500 billion? I'm going to give you guys a minute to try to figure this one out on your own again. There we go. So first thing we would have to do is, of course, adjust the model. What's the model going to become? Perfect. Yeah, we put 4 in there instead of 3. Then what do you do? Okay, we put the 0.5 in for A, and then you divide out the 4. Perfect. So 0.5 divided by 4 is what, 0.125? And then you do have to do the log. Sam, what base is this log? What's going to go down here in our log? Perfect. Remember, it's always from the base of the exponent. The bottom number in the exponent is the base of our log. So then, give me just a second here, Sarah. So Sam, since we're on you here, what's the top? What's going to go in top? The top log up here. What number? Perfect. Good job. And then on bottom? Perfect. Okay, Sarah, what'd you get then for years? 22.8 years. Oops. Instead of, we had, what did we have up here? Where'd it go? There it is. Oops, that's not it. Anyways, go ahead. What was your question? Yep. Which question are you looking at there? Oh, gotcha. So instead of getting to 3 trillion, it only gets to 10% less than that? Well, what you would do, you would start out So for part one, they're just saying you start out with the 3 trillion. But then, yep. Yeah, so what you would do is your model is going to be the exact same. If I make my pen work, there we go. But what they're saying is instead of peaking at 3 trillion, it's 10% less. Well, what's 10% less than 3 trillion? Okay, so that's 3 trillion minus 300 billion, which is 3.0 trillion minus 300 billion is 0.3 trillion. So that starting amount, instead of being 3, is going to be 2.7. Yes. Yeah, you found this was the 10% right here. Yep. Yeah, so we found the 10% and we subtracted that from the original amount. So all that's saying is instead of reaching 3 trillion, it made it to 10% less than 3 trillion, which is 2.7 trillion. So yeah, your model is 2.7 in there instead of 3. You bet. The next section, the next question here is, what if we want this to last to 2062? That'd be 45 years. That'd put me at 89. Social Security can go away. I won't live past 89. That's not the reason we picked 2062, but I'm good with that. So let's say we want this to last until 2062 before it runs out of money. What does the balance need to be? What does the peak balance need to be? So what they're asking us to do is they're asking us to adjust this model. Now this model only has 2 numbers in it. We have the 3 and the 0.913. Which one of those numbers represents a peak balance? Now you remember what this model was created in 2032, or not, 2032, we predicted we're going to reach that peak. And we predicted what would be the balance in 2032? The 3 trillion, right? Yep. So this is the peak here. 2062 is how many years? What I'm asking is what value of t represents 2062? 30. Good. Where did you get the 30? Perfect. We just subtracted 2062 minus 2032, gave us 30 years. So we know that t here is going to become 30. Now remember, it becomes insolvent when A reaches what number? When the balance is what? I heard somebody whispering it there. Insolvent means there's not enough money to pay off. Pay out. That was the 500 billion. Have they mentioned anything about the percent change being changed here at all? So this number here, the 0.913, is the percent change. That hasn't changed at all. In fact, we're looking at number 5 here in the lesson. They're saying it stays at 8.7%. So this does not change. So the only value here that can be changed is the 3, that starting amount. So I'm going to replace that with x. So it's still going to be 0.5 for A. That 0.5 comes from the 500 billion, which is half of a trillion, or 0.5 trillion. X is going to be that starting amount. What goes in for T again? 30. Well, what type of equation is this now? Yeah, you said it. Linear. It still looks like an exponential equation because there's an exponent in it, but where's the variable? Yeah, it's right there. This is only exponential if the variable is the exponent. It's the power of the exponent. It's not. So, in fact, we can take this piece here and we can turn it into a number. We can take 0.913 to the power of 30 and get 0.065. So this is really just 0.5 equals x times 0.065. So this is a linear equation all the way. What's that? And you found that by dividing? Perfect. Yeah. Now I'm going to just keep this in the calculator. I'm going to do 0.5 divided by that answer. So it might be slightly different than what you got, but it's 76.7 is what I'm getting. Oops, I didn't get the 0.5 in there. It is 7.67. Yep. Yeah, 7.67. Now, what does that represent? That is $1 trillion. So we're not even going to have close to half enough if it peaks out at 3 trillion. So what that means is you guys need to work hard to make sure there's an extra $4 trillion in there by 2032 so I can be sure to get my Social Security. Haven't you learned this all about me? Okay. So that's really all of our stuff on the Social Security system here. There are a lot of things that contribute to this. I mean, what are some, first of all, is this definite? I mean, what could change here and why? Okay, perfect. Yeah, that 8.7% could change, that decrease, right? Well, what could change that? Yeah, what could cause it to the balance to fall faster or slower? Well, first thing, of course, investment rates, interest rates, right? They're assuming that they're earning a certain amount on their balance. If that changes, if they start earning more or less interest on that balance, that could change it. Well, Social Security is invested by statute. It has to be invested in treasury bonds, which it's kind of a strange system because what they do is they take your tax money that you pay in your Social Security taxes, and then they actually buy treasury bonds that are basically loaned out to people. So the balance of this is owned by you, pretty much. But yeah, those bond rates and stuff can go up and down from year to year. They are normally pretty stable. They stay in that 3 to 4% rate pretty much constantly. So it's not a huge difference that goes through them. But now there's other assumptions that are being made in here that could change that 8%. What are some things that they're assuming? Well, let me give you an example. Because of my age, I'm 44 years old. I would not be able to draw my maximum Social Security until 67 and 8 months or something like that. Do I have to draw Social Security at that age? No. What could happen instead? Yeah, I could. Both of those are legitimate. I could keep working, or I could be deceased. So for some reason, there may be some reason why people won't draw. Either at that point, maybe things happen that people don't want to retire, so they keep working, or maybe things happen where a bunch of people pass away. There could be the next plague could go through and cut the population down by a significant amount, or something could happen. Now, what are some things the government could do to change this? We could kill more people. I mean, it's true. Increase mortality somehow. The purge. Perfect. Yes, that's exactly it. We have a huge boom going through in Social Security. Maybe people stop having as many children. Birth rates change. Uh, in China, there are laws governing how many children you can have. I believe you're only allowed to have up to 2 children. If the first child is a male child, you can only have one. If the first child is female, you can have a second child. Yeah. Well, the reason they changed that, it used to be for a lot of years you were only allowed to have one child, and there was a huge problem with female children being abandoned because there's still a huge family agricultural economy. So they wanted the male children to work for the family farms and whatever, the family businesses. So they changed that so that they would hopefully limit that issue. But yeah, I'm not a I'm not a huge I don't know if I would necessarily support our government trying something like that, but there is a social trend. I know I haven't looked at it for a few years, but in 2008, the trend was the average married couple only had like 1.7 children. So that was less than the 2 people. So the number of children is dropping. Okay. Other things that could happen? Probably the most practical one. There's 2 of them that are probably the most practical. What could the government increase that would change things? Taxes would be one. What else could they increase? Well, to keep me, if I started drawing at 67, what could they change to make me draw less Social Security? Perfect. Increase the age. So they either increase the amount that they take out of your paycheck for taxes, or they could increase the age that you draw. Tell me that I can't draw until 70 instead of 67 and a half. They could decrease what? There you go. The payments, the amount that you're going to get. That's a big one that they've actually discussed, is if you have money put away for your own retirement, of decreasing how much you can actually draw out. Okay, so there's a couple of things I wanted to show you based on this. We talked about half-life and its relation to these exponential models. And I'm going to give you a model, and of course, if we're talking about exponential decay, is half-life a big deal? If we're talking about exponential growth, it would be doubling time, right? So let's take a look at, of course, that would be growth. Let's take a look at converting back and forth between these models. If I have a half-life, let's just look at your retirement fund. And you're drawing out at a rate so that it is decreasing at 12% per year. I'm going to do two things. One, I'm going to find the half-life. And two, I'm going to create a half-life model. So first, to find the half-life up here, I need to first find the exponential model. It's an exponential model because I'm given a percent decrease every year. So what is that exponential model going to look like? Well, I need to tell you what the starting amount is, don't I? Let's say we're starting at $200,000. So our exponential model is going to be A equals the starting amount of 200,000 times what goes in our parentheses? Perfect. One, you got it. So it'd be 1 minus 0.12. So that's going to be 0.88 t. Perfect. So a half-life is going to be the time it takes for the amount to get down to 100,000. Yep. Now I gave you this $200,000 balance, starting balance. Did we really need a starting balance to find a half-life? You can just always put in 0.5 for the amount, exactly. Because when we divide here, this is going to be 0.5 equals that 0.88 to the power of t. When you're talking about half-life, yes. Yeah, the half-life does not depend on the starting amount. So then from this point, how are we going to solve it? Yep. It's going to be log base what? 0.88. The base of our exponent is 0.88. So yes, to put that in the calculator, we're going to do log over log. Which number goes on top? What number goes on top in our log here for doing this log? 0.5. Good. And what goes on bottom? 0.88. 5.4? Let's go 5.422 equals t. Sure. Yep. 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 All right, which problem are you looking at here? Yep. So in 2B, they're looking at what would the value in 2040 be. So you have to actually find the value with the model. So the model is going to be, give me about 15 minutes. The model originally would be 1 times 0.913 to the power of t. And t starts, t is going to equal 8 to the 2040. Okay. Yes, it's going to be 2.7, right? It's 10% less. 1303 billion? Or 1.303. Okay, 1.303. I know what you're talking about. Yep. Okay, gotcha. And this one is what? 14 what? 1.448. Okay. So then what it's asking you is what is the 1% less? Now this goes back to that formula you were talking about before. It's the, yep. So, and it doesn't matter which one you put in here. Whichever one goes first should go down here. And since this is the one we did first, this was the original amount, goes here. That's the old amount. This is the new amount after the decrease. So that goes here. It said no to you? Okay, you may have put the 1.303 on bottom. So you subtract there, you get the 1.445 divided by 1.448, because it should come out to be 10%, exactly there. I'm guessing you had the 1.303 on bottom. Yeah, so you have to have the 1.448 on bottom. Because, yep. Well, let me show you something here. In these models, when you go to solve this, you've got 0.913 to the power of 8 here, both times, right? 0.913 to the power of 8 is going to be 0.483 no matter what. So all that has changed here is this number. And since that number has decreased by 10%, the balance will also decrease by 10%. If we doubled the starting amount, if we doubled this to 6 billion instead of, or 6 trillion instead of 3 trillion, the amount after 8 years is going to be double what we had here after 8 years. Does that make any sense? That's one of the neat things about the structure of a exponential model is the behavior of the starting amount does not affect the half-life, but it does affect the balances, but the balances are affected by the same percent as whatever that starting amount is. Yeah. Exactly. Yep. Well, the next one's a little different because the actual rate of decline is 10% greater than 8.7. So here we have 8.7%. To find 10% greater. Now we're not changing the starting amount, we're changing the rate of change. To increase something by 10%, we multiply by 1.1. Where does 1.1 come from? There you go. It's 100% plus 10% is 110%, which as a decimal is 1.1. So this means the 8.7% times 1.1 is 9.57%. So that's going to be your rate of change that you use. You're just going to have to calculate these out because that's going to become totally different. Changing that by 10% is going to do more than changing the balance by 10%. These will take a little bit of time to get used to. Yeah, 10% was the actual answer for. Oh. Yeah. You could have done, I technically probably did this backwards. I should have done the 1.303 minus 1.448, but it still should have been over 1.448. And this would have been a negative number on top. So technically it's a negative 0.1 that we get for the change, but it's a negative 10%. Okay. Go ahead. Okay, can you print it off? Yeah. When did you email me? Okay. I haven't checked Quantway since like last Thursday. So I will make sure I check it and see. I'm still adjusting to the new system, so I will make sure I get it. If you don't hear a response from me by Wednesday, let me know and we'll adjust how we communicate on that. But I'll look. If you can print it off and redo it and send it to me, that would be wonderful. I will look at it and see if I can figure out how to change it so you have more attempts on it. We do have the out of class exercises for M6, by the way, that are set to be due tomorrow. Oops, that's Tuesday, November 7th. And then the preparing for next lesson for M7 is also due tomorrow. Yeah, the OCE for M7, which is what we covered today, that'll be due on Thursday. And that's November 9th. And then the PNL for M8 is going to be due for Thursday. So finish these up. This is what was assigned from last Wednesday. So you finish those up and have them submitted tomorrow for me. And this is going to be the new stuff from today that I'd like to have you work on and submit for me for next class. Now, since we have about 5 or 6 minutes left here, there is something very powerful I want to show you about these exponential models. Not to pry, but how many of you are under 25 years of age? Just a show of hands. Perfect. How about under 22 years of age? Oh, this is perfect. So we're going to work at 22 years old. Well, we just talked about the Social Security system. If you can retire at age 67, which is going to be slightly older than that by the time you guys get there. But let's go off of that right now. That is 45 years. What I want to look at, let's say that your first year out of college, a lot of students, they get out of school. You were talking about having to choose between ramen noodles and food and medications, for budget reasons. You get out of school, you've been living cheaply for a couple of years, and now you get that first good job. A lot of people want to move into a nicer apartment. Maybe they want to get a nicer vehicle. Whatever, they upgrade their lifestyle. But what if you stayed living cheaply like you are now for a couple of years? In that first year of working, how much money do you think you could save up and put away? A lot? You think you could do $5,000 a year? Probably not. Okay, what balance do you think you could do? Yep. 35 to 40 grand. That'd only be like $200 a paycheck. Yep. Okay, well, let's try that. If you put it away for 45 years, the average return on an investment on a retirement account over 45 years is between 12 and 13% per year. So let's say that we're going to be a little conservative. We're going to do a 10% compounded annually. So remember, our model for that is your starting balance times 1 plus 0.10 divided by, since it's compounded annually, n would be 1, right? Once a year, to the power of 1 times 45. So again, I'm just going to 1 times 45 is 45. So I'm going to punch it in like that. So 5,000 times 1 plus 0.1 divided by 1 to the power of 45. If you did that at 22 years of age, at 10% interest, at 67, you'd have $364,452. And 42 cents, yes. So over $350,000 off of that one $5,000 investment. 45 years. Well, we'll bring that up here in just a second. What if you waited till you were 32 years old and then decided, okay, now I'll start worrying about retirement? Well, it's going to be how many? Yeah, how many years would that be? Instead of 45, it's going to be 35. Yep. Anybody want to guess at what this is going to be now? It's going to be less. You're 140,512. Guess, not no. So anyway, it's almost cut to a third. By waiting that 10 years, it's down to between a third and a half of what it would have been. Probably, yes. But I'm just going off of that same investment. Let's say you waited till you're 42 years old. Yeah, thanks. I'm 44. It does, definitely. So it'd be 25 instead of 35. You can see you only get 54,173. At least two. My daughter's 19 and my son is 15. 15. Sorry. So anyway, I just wanted you to show those examples. Since you guys are young, once you're out of school and start working and have income coming in, the sooner you think about retirement, the better off you are. Okay, it is about that time, so I'll stop talking for the day. We'll see you guys on Wednesday. Again, yes. Oops, I lost you. The interest rate, if you're listening to the recording, the interest rate, you get a better interest rate by just changing what you invest in. So go to an investment plan or invest in stocks instead of bonds or whatever. You'd have to talk to an investment person as to how to increase that interest rate. Okay, that is it. So we will see you guys on Wednesday.